In this video, we would like to learn about the coefficient of determination. Precisely, when we look at the amount of information we need to predict the response variable accurately, let's say ideally it's 100%, and we would like to measure the proportion or the amount of total information that we need to make predictions of the response variable that are provided by the explanatory variable. The go-to statistic is the coefficient of determination written as R squared. Why R squared? Very simple, because it is the square of the sample correlation coefficient value that we used to get in earlier videos. So, what are the range of values of R squared in this case? The range of values of R squared is from 0 to 1. Since you're squaring, it's never going to be negative. And if R squared is equal to 0, it means the explanatory variable has no value or offers no information in terms of predicting the response variable. Otherwise, if the R squared is equal to 1, then the least squares regression line provides 100% of the information we need to explain the changes in the response variable. The closer R squared is to 1, the better the regression line explains how changes in the explanatory variable impacts the value of the response variable. So let's give an example, or consider an example here, where we are required to match the coefficient of determination to the appropriate scatter diagram. The scales on the x-axis and y-axis are the same for each scatter diagram. So I have R squared equals 0.9298, R squared equals 0.65, and R squared equals 1. I will start with the perfect condition, R squared equals 1. That would be the very first one. That is because all points lie exactly on that line. So every information we need to predict the response variable, the explanatory variable provides everything, 100%. Then, the next step would be, I can observe that if I look at this 2, this has the points more closer to the point than this guy, which has an attempting or a potential outlier here. So I can definitely tell that after 1, 0.98 should go to this guy, so 0.8, because it is the next in line where all the scatter points are very, very, very close to the line of best fit. And finally, this is option B, which is 0.65, and the drop could have been due to the presence of this guy right here. With that question completed, we proceed to the next part. In this example, we're told that the chapter 4 data sets, which is in columns R and S, represent the weights of various domestic cars and their miles per gallon in the city for the 2008 model year. For this data, the least squares regression line is already given. It is y at the predicted value equals negative 0.006x plus 41.926. Now we're told that the 12th car weighs 3,425 pounds and gets 13 miles per gallon. Question A. What proportion of the variability in miles per gallon is explained by the relation between weight of the car and miles per gallon? To answer that question, we need to simply compute the coefficient of determination. And to do that, coefficient of determination is equal to R squared. So R squared, remember, is the correlation coefficient square. How do we do that? So what we will do is, let's look at the data set in StatCrunch. So I'm going to go to StatCrunch. Let me minimize this. So right here on the screen, I can see the weight, I can see the miles. I'll go to statistics, go to summary statistics, go to correlation, and I would like to choose both options. I can see there's weight in pounds and miles per gallon. So let me scroll down. Weight in pounds and miles per gallon. And I would like to compute the correlation coefficient, which is negative 0.912. So I have that here. So that will be, excuse me, that will be equal to negative 0.912 all square. So if I square this, I should get a positive number. This is equal to 0.831744, which is approximately 0.83. So the question back again is, what proportion of the variability in miles per gallon in the city is explained by the relationship between both the weight and the miles per gallon in the city? This would be approximately 83%. Then, question B, we are to compute the coefficient of determination of the expanded data set. What is the expanded data set? Recall that we're told that a 12th car weighs 3,425 pounds and gets 13 miles per gallon. What we're going to do in order to get the expanded data set is to expand that data set, that existing data set, by including 3425 first in the weight here. So I'm going to go here and put 3425. Then I'll move here. Let me X this out. And then right here, for miles per gallon, going back, I want 13 miles per gallon. So I want 13, and then drop that down. And once that is done, I would like to compute the coefficient of determination. So what I will do is to go to Stat, go to Summary Stats, go to Correlation between, let me make sure of that, between weight in pounds, X and Y. So I have this. All right, and compute again. So this time, the correlation is negative 0.745. Okay, so I will take that back here. So the coefficient of determination in this case is negative 0.745 all square. And the result of that is 0.555, or approximately 0.56, which is 56%. Now we're ready to answer the last part here, which is, what effect does the addition of the 12th car to the data set have on R square? We can see that there has been a significant drop. So we can say that it decreases R square. Then, based on this decrease, or the effect of this added value, this pair of values, we can answer question C. Is this point corresponding to the 12th car influential or an outlier? The correct answer is that no, it is not influential. Rather, it is an outlier. Rather, it is an outlier. That is what it is. That's what an outlier does to the coefficient of determination. It can have a significant effect on it, which indicates that the coefficient of determination is not robust. It is not a robust statistic.